going to pick up where we left off before spring break. And we're going to finish the chapter 7. We're going to talk about stoichiometry. Stoichiometry is a method that we use to determine unknown quantities from a chemical reaction. The most important thing about it is that we need to use a balanced equation, balanced chemical reaction. And once we have that, we can use the equation to determine unknown quantities from another quantity that we know. So if I know an amount of a reactant, I can relate that using the balanced equation to any other reactants or any products in that same equation. How do I do that? Well, here's an example of a chemical reaction. As you can see here, once again, we start with a balanced chemical equation. I cannot stress that enough. It has to be balanced. If it isn't, then your calculations are off. You can see, and we've talked about this before, you can see that there's numbers in front of every molecule in this chemical reaction, in each reactant and each product. Those numbers, we call them molar coefficients, and they provide a way to relate each amount of each molecule. They give us a relationship between molecules in this reactant. For example, I can say that for every 2 moles, and remember these are molar coefficients, you cannot do this with grams. For every 2 moles of ethane, I burn 5 moles of oxygen. That's what the 2 and the 5 tell me. And I produce 4 moles of carbon dioxide and 2 moles of water vapor. So these coefficients tell me how many moles of each substance is involved in the equation. And that's an important fact because I can then relate known amounts to unknown amounts. Here's an example of a typical stoichiometry question, and we'll start with easy steps and then we'll build up from there. Given the following equation, how much water vapor is generated by using 2.4 moles of oxygen to burn excess of ethane. The excess part tells me that this isn't going to run out. The oxygen is going to run out first. Excuse me. This is a combustion reaction, by the way. I have oxygen burning and I produce CO2 and H2O. Excuse me. So how do I start? I'm given that I start out with 2.4 moles of oxygen that burns and produces an unknown amount of water vapor. But from the balanced equation, I can see that for every 5 moles of oxygen, I get 2 moles of water. Now I don't have 5 moles, I start out with 2.4 moles, which is a little less than half of 5, which means that I'll get a little less than 2, just from looking at this balanced equation. So here's how I set it up. I'm looking for, I don't know, the moles of water. That's a question mark or an X, whatever you want to put there. But I'm looking for moles of water from moles of oxygen. So I start with my moles of oxygen, 2.4 moles. This is what I have of oxygen. And then I set up the molar ratios, the coefficients. I set them up as a fraction, as a conversion factor in such a way that I can cancel my moles of oxygen and I'm left with water. So I need to put moles of oxygen at the bottom because that will cancel with moles of oxygen at the top. And then I have moles of water up on top, which is the unit that I'm looking for. Do not skip this step. Be very conscious about it. Write out the fractions and the units because they will help you keep track. My moles of oxygen cancel. I'm left with moles of water, so I can do this math very easily. 2.4 multiplied by 2 divided by 5 gives me 0.96 moles. Self-check. Is this number correct? Yes, it is, because we know that for 5 moles of oxygen, I get 2 moles of water. I have just a little less than 5, so I should get a little less than 2, which is, or a little less than 1, I'm sorry, which is 0.96 moles. So I have done this correctly. If you had flipped these two, you would get a larger number than that. So you can double check your answer saying, okay, I made a mistake here because I did not get half of 2 like I was supposed to. Let's look at another example. How many moles of ethane, C2H4, must be burned in an excess of oxygen this time to get 3.4 moles of CO2? So now I'm looking at the other two compounds. I have an amount of CO2 that's being produced, and I have to figure out how much ethane was burned to produce that amount of CO2. So you can relate anything. If you know an amount of product, you can figure out how much reactant was there to begin with. Or if I have an amount of reactant, I can figure out how much product I'm going to make. So how do I set this up? Once again, the excess O2 tells me that the ethane is going to run out first, so I don't have to worry about the oxygen. Here's how I do it. I am looking for the moles of ethane, so that's why there's a question mark there. That is equal to, I need to relate it to the CO2 because that's where I'm given moles of CO2. That's the amount that I'm given. So I have 3.4 moles of CO2, and I need to find a way to relate these moles back to moles of ethane. And I do that by using the balanced chemical equation, because I know that for every 4 moles of CO2, I burn 2 moles of C2H4. What if I don't have 4 moles, I have 3.4 moles. So I should get a little less than 2, obviously. 3.4 moles of CO2. I set up my conversion factor from the molar coefficients in such a way to get rid of my CO2 moles. I write moles of CO2 at the bottom and moles of C2H4 on the top because that is the unit that I want to be left with. My moles of CO2 will cancel, and I'm left with moles of C2H4. I can do the math very easily. 3.4 moles of CO2 multiplied by 2 moles of C2H4 divided by 4 moles of carbon dioxide gives me 1.7 moles. Now stop and ask yourself, does this answer make sense? Well, yes, it does, because for every 2 moles of ethane, I would get 4 moles of CO2. But I have 3.4 moles, which means I would have started with less than 2 moles of C2H4 and about 1.7. That is reasonable. Once again, if I had flipped these two numbers, I had 4 up on top and 2 at the bottom, I would get a much larger number than 2, which would not make sense. And if you had done that and stopped to think about the relationship, then you'd say, oh, I've done this wrong. I need to check these numbers. I need to check my math. Here are the steps. This is the general outline of the steps that we need to go through to solve stoichiometry problems. You may not need to use these steps every time that you do a stoichiometry problem, but it's a thorough list. And for some problems, you'll have to go through all of these. And for some others, you may start here and do just 4 and 5, etc., etc. The first thing that you need to do, is to determine if the equation is balanced. Without a balanced chemical equation, you cannot relate those molar coefficients correctly. You need to at least check if the equation is balanced. Sometimes it's going to be balanced already, so you don't need to do anything. But if it isn't, then you're going to have to balance the equation first. Then you check to see if the known quantity is in mass in grams or in moles. If it is in grams, you're going to have to convert it to moles because you cannot use the balanced equation if you have a mass in grams directly. That equation only relates moles of one substance to moles of another substance, not grams of a substance. Therefore, you have to convert anything that's in grams, you have to convert it into moles. We know how to do that by using the molar mass. We've done that tons of times. And we'll look at some examples in the following slides. But if you have a mass in grams, you are going to better just get used to it. Convert all your mass in grams into moles. Then you're gonna have to determine the limiting reagent. We'll talk about that once again, a few more steps here. The limiting reagent is that reactant that will run out faster, will run out first. Once you determine that, you can balance the equation, use the balanced equation to determine the moles of the unknown quantity that you want from the moles of that reactant that will run out faster. And then lastly, if it asks you to calculate not only the moles of the unknown value, but a mass in grams, you can then convert those moles back to grams by using the molar mass of that compound. So this is once again a comprehensive list. You may or may not be using this every time, but you will be using at least a few of these, so get used to what the steps are. Let's look at one more example here. This is with moles. We have a word problem, and we have to translate it. We have to write the chemical equation. We have potassium chromate reacts with lead 2 chloride. We need to write the balanced equation and determine what products would be produced and how many moles of the solid product would result from 2 moles of lead 2 chloride with an excess of potassium chromate. Chromate is a 2 minus, potassium is a plus 1, so I need 2 potassiums for every chromate. The lead 2, this 2 tells me the charge on the lead, so lead is a 2 plus in this case. Chloride, it's a minus 1, so I need 2 chlorides to balance my lead. That will be the reactants. The products, we basically swap. It's a double displacement reaction. I react potassium, or potassium will combine with chloride. This is a plus 1, this is a minus 1, so this just forms KCl. And lead is a 2 plus, chromate is a 2 minus, so this will also form a 1-to-1 compound, so lead chromate. And here's the formula. So as you can see, I said chromate is a 2 minus, potassium is a plus 1, so I need 2 potassiums for every chromate, potassium chromate, plus lead chloride, lead 2 chloride. The 2 up here tells me lead is a 2 plus, chlorine is a minus 1, so I need 2 chlorides to balance my lead. Then here, potassium is a plus 1, chlorine is a minus 1, so this is a 1-to-1 ratio, KCl. Lead chromate, lead 2 chromate, the lead has a 2 plus charge, chromate has a 2 minus. I don't need to mess with any coefficients because the charges balance out here. To balance the equation, all I have to do is put a 2 in front, and remember, because I have 2 chlorines and I have 2 potassiums here, instead of putting K2Cl2, we don't do that because we use the smallest number ratio between elements in a compound, which is 1-to-1 in this case. But to make sure that I can balance them, I put a 2 as a coefficient in front of the molecule, the whole molecule, not as a subscript here. Those subscripts are only used if I'm manipulating one element at a time. Like here, for example, I just need to manipulate potassium to balance the charge, so I put the 2 here. if I do a 2 up front here, then I get 2 for potassium and 2 for the chromate. So that I can't do that. All right, now that I have this reaction, I need to figure out, the question also asks me, how many moles of product, the solid product, would I get from 2 moles of lead 2 chloride, which is my reactant here. And I know that KCl is in aqueous solution because potassium, anything with potassium and chlorine is soluble, but lead 2 chromate isn't. That's my solid compound. Basically, it's asking me, if I have 2 moles of lead 2 chloride, how many moles of lead 2 chromate will I make? Well, this is how I set it up. I am after how many moles of lead 2 chromate will I need. That is equal to, I start with the moles of my reactant that I'm given, 2 moles of lead 2 chloride. And then I set up my ratios in such a way that I will cancel my moles of lead 2 chloride and I'm left with moles of lead 2 chromate. So it's a 1-to-1 ratio. For every mole of lead 2 chloride, I make 1 mole of lead 2 chromate. And here it is. 1 mole of lead 2 chromate for every 1 mole of lead 2 chloride. These will cancel, leaving me with the moles of lead 2 chromate at the top, which will be 2 moles, because it's a 1-to-1 ratio. This was a little more involved because we had a word problem. We had to translate it into formulas. You do the worksheets. You have a bunch of problems on how to do those. It's important that you know how to decipher the names of, so to go from the name of a compound and try to figure out what the formula of that compound is, having a neutral charge and all of that, it's important to do. So you have a few of these in the worksheet. Go ahead and work on those. And please ask questions if you need to. Just reach out to me, email me, and I will be more than happy to let you know if you've done them correctly or not. All right, now what happens if instead of having moles, I'm not given moles anymore, but I'm given a mass in grams? I have an extra step that I need to add. Here's an example. This should look familiar. So this is my balanced equation from a few slides before. How much water vapor would be produced by burning 12.4 grams of ethane in excess oxygen? So now instead of having moles of ethane, I have grams of ethane. I cannot use the mass in grams and then set up my ratios here like I did a few slides earlier, because these coefficients only relate the number of moles, not the mass in grams. The first thing that I need to do then is to convert this amount in grams to an amount of moles. And I can do that. I know how to do that because I can find the molar mass of C2H4 and I can convert that to moles. Here it is. I need to figure out how many moles of C2H4 I can, 12.4 grams gives me. I start with that amount, 12.4 grams. Once again, do not start with the molar mass. This is your conversion factor. Always start with the amount of grams that you are given in the problem. Do not start, never start with 28.24 grams, for example. That is not how you start. That's your conversion factor. You always start with the amount of grams that you are given in the problem. This is what you calculate by adding the masses of each element. This is the mass that you are given in the problem. So always start with that. And then you can write the molar mass as a fraction in such a way to get rid of the grams. I know that 1 mole of C2H4 weighs 28.24 grams. This is how you write it. My grams will cancel out, leaving me with moles at the top, and it gives me 0.439 moles of C2H4. Now that I have moles of C2H4, I can go up here and use this balanced chemical reaction to relate the moles of C2H4 to moles of water vapor. Pretty easy now. Okay, I go to the equation to determine the moles of water. How many moles of water do I have? Well, I start with the amount of C2H4 that I calculated, this many moles, so 0.439 moles of C2H4, multiplied by the molar ratios of these two compounds. I want moles of water on top, so I write 2 moles of H2O over 2 moles of C2H4. So for every 2 moles of H2O that I form, I burn 2 moles of C2H4. That's what this is telling me. Moles of C2H4 will cancel out, leaving me obviously with 0.439 moles of water, because this 2-to-2 ratio is the same as a 1-to-1 ratio. Now that I have the moles of water, I can convert this to an amount in grams by using the molar mass of water. So I convert moles back to mass by using the molar mass of water. 0.439 moles, and then I write the molar mass of water in such a way to cancel my moles. 18.4 grams of water give me 1 mole, or 1 mole of water weighs 18.14 grams. Moles of water here will cancel out, and if I do the math here, I get about 7.97 grams of water. This is how I figure out stoichiometrically how many grams of a substance are formed by starting with an amount in grams of a reactant. I could have done this backwards. I could have started with an amount of grams of a product and figured out how many grams of reactant I used up. It's the same procedure, you just go back and forth depending on which direction you are asked to go. But the procedure is the same. Remember, the first thing that you need to do, obviously, is balance the reaction, but then you need to convert those amounts of grams into moles to use these coefficients. You cannot use them if you have amount in grams. For example, if I were to go over here, I cannot use 12.4 grams because these are molar coefficients. That is why I say you write the units out. A lot of students would just write 2 H2Os and 2 C2H4s. That is not the correct way, because you would be tempted to write grams over here and not knowing that this isn't really set up for grams but it's for moles, you could continue with a problem. But if you wrote out that this is a molar fraction, so 2 moles of water over 2 moles of C2H4, if you had grams over here, you couldn't cancel the grams with the moles, so your units wouldn't cancel out. Then you'd think, oh, I need moles here, so I forgot one step. I need to go back up here to convert it to moles. Let's look at another example. For the reaction of lithium with chlorine to form lithium chloride, how much chlorine in grams would be needed to react with 0.6 grams of lithium? Here is my reaction. I have lithium. Lithium in its elemental form is a solid. It's a metal solid. Chlorine in its elemental form, it's Cl2 as a gas. These two combine to give me lithium chloride. Lithium is a +1 ion. Chloride is a -1 ion. So is LiCl. That's the formula. Now, because I have two chlorines, I need to put a 2 up front here, which makes 2 chlorides, but then it changes the lithiums, and I can go back here then to balance the lithium out and put a 2 in front of the lithium. This is my balanced chemical equation. Now that I have this, my first step, I look over here and I see, oh, I'm given an amount in grams of lithium. I cannot use this with the chemical equation because it's in grams. I have to first convert it to moles. moles of lithium. How do I do that? Well, I know the atomic mass of lithium, so I can convert it to moles by using that. Here it is. How many moles of lithium? That's what I'm looking for. I start with my amount in grams. Always start with the amount you're given in the problem. Never start with the atomic mass or molar mass. I know, so I have 0.6 grams of lithium. I know that 1 mole of lithium weighs 6.94 grams. I want the grams at the bottom so they can cancel with the grams on top, and moles, I'll be left with moles. This will be 0.0864 moles of lithium. Now that I converted the amount of grams into moles, I can go up here and relate it to chlorine and to lithium chloride because I know the molar coefficients from the balanced equation. I need to figure out how much chlorine in grams would be needed. Now I can't do grams right away, but I can figure out from the equation how many moles of chlorine. Here's how I do that. I use the equation to determine the moles of chlorine. Moles of chlorine are equal to, I start out with the moles of lithium, so 2.0865 moles of lithium, multiplied by the ratio between these two, molar ratio. I know that for every mole of chlorine, I use up 2 moles of lithium. So I have 1 mole Cl2 over 2 moles of lithium. My moles of lithium will cancel out. And I have 0.0432 moles of Cl2. But it asks me to find it in grams, not just in moles, so I cannot stop there. The last step then would be to convert this amount of moles of chlorine to grams by using the molar mass of chlorine. I go back here. How many grams of chlorine? That's equal to the moles of chlorine that I just calculated multiplied by, so here's how I set up my conversion factor for the molar mass. I know 1 mole of chlorine weighs 70.9 grams of chlorine. You can figure this out because each chlorine is 35.45. That's what they weigh. I have 2 of them, so multiply that by 2 gives me 70.9 grams. Moles of chlorine will cancel with moles of chlorine, leaving me with grams. And I multiply these two numbers, giving me 3.06 grams of chlorine. That is how much chlorine I would need to react with 0.6 grams of lithium to produce lithium chloride. Okay. The next step that we need to talk about is the limiting reagents. And as I said, limiting reagents are those reactants that will run out first. If I have this set up, for example, I have these two, they're supposed to be red, but they look orange, more orange balls, and then I have these blue balls. How many of this configuration could I make given these components? Well, I can only make 2 of those because I only have 2 red balls or two orange. I am limited by how many of these I have. I use this analogy and it's pretty corny, but it seems to work. So if you're at a dance, high school dance, and you have 5 boys and 12 girls, how many dancing couples would you make? You would make 5 dancing couples because you only have 5 boys. And they limit how many couples you can make. The same idea works for the limiting reagent. The limiting reagent will limit how much product you make. You cannot make any more product than it's allowed by the limiting reagent because you'll run out. You'll have some left over of the other reagent. This is the one that runs out faster, the red balls or orange, whatever, and then you'll have some left over of the other reactant. But you cannot make any more product because you've run out of one of the reactants, which is called the limiting reagent. you will be able to tell if you have one of these limiting reagent problems by looking at the problem itself. If you are given an amount in grams for both reactants, that means you have to first determine which will run out first. If you're given only one amount in grams and you're told in the previous problems that we were doing, we were told that it's in the other one is in excess, then that means you don't have to worry about the limiting reagent, because the one that you're given is going to be the limiting reagent if the other one is in excess. But if you're given both two amounts for your reactants, then you have to figure out, okay, one of these is going to run out faster and I need to figure out which one. You cannot determine it directly by just looking at the amount of grams, because it depends on the balanced chemical reaction and it depends on how many moles you have of each reactant, not the grams. So let's look at this example. If you use 2.4 grams of NaOH, sodium hydroxide, to neutralize 3.7 grams of hydrochloric acid, HCl, how much sodium chloride would be produced in moles? Okay, here's my equation. I have sodium hydroxide reacting with HCl to give me NaCl, sodium chloride, and it also forms water. This is an acid-base neutralization reaction. I have a base and I have an acid, gives me a salt and water because it's a strong base and strong acid. I don't need to balance it, it's already balanced. So I have one sodium here, one chlorine, two hydrogens, one oxygen. So I'm good. I don't need to do anything to balance. The first thing then that I need to do is figure out how many moles of NaOH do I have and how many moles of HCl do I have. I figure that out by using the molar mass of each. If you do that, you will figure out that the molar mass of sodium hydroxide is about 40 grams. So I know 1 mole of NaOH weighs about 40 grams. Once again, start with the amount of grams that you are given in the problem, not with the molar mass. So 2.4 grams of NaOH multiplied by 1 mole of NaOH weighing 40 grams. My grams will cancel and I'm left with moles. 2.4 divided by 40 gives me 0.06 moles of NaOH. This is how much NaOH I have in moles, not in grams. I do the same thing for HCl. Moles of HCl, I start out with the amount of HCl that I'm given, and I know that 1 mole of HCl weighs 36.46 grams. I write my grams at the bottom so that they can cancel with the grams at the top. So the grams cancel, leaving me with moles at the top. If I do 3.7 divided by 36.46, I get 0.101 moles of HCl. Now, because I have a 1-to-1 ratio for this equation, everything is a 1-to-1 ratio, I can see that if I had 1 mole of NaOH gives me 1 mole of NaCl. If I only have 0.06 moles of NaOH, that will give me 0.06 moles of NaCl. Same thing if I go over here and do the same thing with moles of HCl. 1 mole of HCl gives me 1 mole of sodium chloride. What if I had 0.101 moles? That will give me 0.101 moles of HCl. Because moles of NaOH produces less NaCl than moles of HCl. So if all of my NaOH is used up to produce NaCl, then that will run out first. Then I cannot make any more NaCl than I have NaOH because this will run out. Therefore, my NaOH is the limiting reagent, and this is how much NaCl would be produced in moles. 0.06 moles because it's a 1-to-1 ratio. Now, what happens if I don't have a 1 to here? I had a 1-to-1 ratio between all of my reactants and products. What if I don't have that? Things get a little more complicated, but not by much. So let's look at the same type of problem with the same numbers, initial numbers, but now so I have NaOH, but instead of HCl, I have sulfuric acid, H2SO4. How much Na2SO4 would be produced in moles? I go through the same steps. You got it. So first thing I have to do is write out my chemical equation. I start out with sodium hydroxide added to my sulfuric acid, and it gives me sodium sulfate and water. Note that for the sodium sulfate, I have to have this 2. Sodium is a +1, sulfate is a 2-. You've got to learn those signs, the polyatomic charges. So I need 2 sodiums to balance out my sulfate. Then because I have 2 sodiums here, I have to put a 2 in front of NaOH here. I don't need to mess with the SO4. Think of this as a unit. I have 1 SO4 here and 1 SO4 here, so that's balanced out. I have 2 hydrogens here and 2 hydrogens here. That's 4 hydrogens and 2 oxygens. So all I need to do is put a 2 in front of H2O, giving me 4 hydrogens and 2 oxygens, and this is balanced. Now that I have this balanced, all I have to do is convert these amounts from grams to moles. We already looked at this. We figured it out in the previous slide. So 2.4 grams of NaOH divided by 40 grams per mole gives me 0.06 moles of NaOH. If I do the same thing now I can figure out by these moles of NaOH how many moles of sodium sulfate I will make. So I can go use the equation up here, figuring out I have 2 moles for every 2 moles of NaOH, I make 1 mole of Na2SO4. So how many moles of sodium sulfate will I get if all of my NaOH reacts? I start out with the amount of NaOH, 0.06 moles of NaOH, multiplied by 1 mole of sodium sulfate on top, divided by 2 moles of sodium hydroxide. So 1-to-2 ratio. My moles of NaOH will cancel. That is why it's so important to write out the units. Do not skimp or get lazy on it. Write out not just the units, but also the compound. That will help keep track. So my moles of NaOH cancels out, and I'm left with moles of sodium sulfate at the top. So I will make half the amount, 0.03 moles of sodium sulfate, if all of that 0.06 moles of NaOH is used up. Now let's look at what happens when we use the the sulfuric acid. First thing I need to do is convert this into moles. Whoops. I'm out of order, sorry. So if I want to first calculate the amount of moles, I use 3.7 grams of sulfuric acid. I know 1 mole of sulfuric acid weighs about 98.08 grams. I write this conversion factor in such a way to get rid of my grams. Grams will cancel with grams, leaving me moles at the top, and I get 0.038 moles of H2SO4. This is how much I have. Now you might be tempted to think that, let's go back here, tempted to think that because I have 0.06 moles of NaOH and only 0.038 moles of H2SO4, that this is going to run out faster. The thing that we have to be careful with here is that we don't have a 1-to-1 ratio anymore, and that changes the things a little bit. So I need to figure out if I used up all of this amount of sulfuric acid, how much sodium sulfate will I make? So here it is. I go back and I use the equation, 0.038 moles of H2SO4. It's a 1-to-1 ratio for these two. 1 mole of sodium sulfate is made for every 1 mole of sulfuric acid that reacts. My moles of sulfuric acid cancel, leaving me moles of sodium sulfate, and I would make 0.038 moles of sodium sulfate. If this ran out first, I would be making 0.038 moles of sodium sulfate. But if I used up all of my sodium hydroxide, I would only make 0.03 moles of sodium sulfate. This will be my limiting reagent because I make less using all of my NaOH. I make less of my product than if I used up all of my H2SO4. So from the moles of Na2SO4 that we could make from sodium hydroxide were only 0.03, whereas from the sulfuric acid, I would make 0.038. So this is a larger amount, which means that my NaOH will run out first. It will run out faster. Do not, and that's what I mean, do not be deceived by the fact that, oh, this is a smaller amount, because for the NaOH, we have a 1-to-2 ratio, whereas for these two, we had a 1-to-1 ratio, and that does change things. So you first, for these types of problems, you have to convert these amounts to moles. Then you figure out by using the equation how much product would each of these make if all of them were used up, and then compare the one that gives you the smallest amount of product. That will be the one that will run out faster. That will be your limiting reagent. If they're all 1-to-1 ratio, then you don't even have to worry about figuring out both of these moles, because you can see it just like we did with sodium hydroxide and HCl, that the one that was the least amount will give me the least product because it's a 1-to-1 ratio. But here, for this reaction, it isn't. Then I had an extra step of figuring out how much product I was going to get from each reactant, and that would tell me which one would run out faster. I will be making a few more of these problems, videos of a few more of these problems, and I will put them up on either JetNet or a YouTube link, and you can go on there and review those types of problems. And I will also have some that you could work. There's some on your worksheets, and you can work on those independently on your own and try to figure them out as well. And if you get stuck, once again, please ask. It is very important, especially now, because we are going to a completely online format, that you do that. Communicate with me. Then the last part of chapter 7 that we're going to talk about is the percent yield. It's very similar to a mass percent, but instead of using mass of components and mass of solution, we're using slightly different we're using an amount in grams of the same substance, but one is theoretical and one is experimental. In the problems that we've been doing so far, we've been assuming that we have 100% efficiency, but that is not true. That is not possible due to the second law of thermodynamics, and we're not going to get into that, why that is, but we can never get 100% efficiency. Think perpetual mobile, right? We cannot get 100%. So what we calculate then by using the chemical equation, that is a theoretical yield. We've been saying if the amount of reactant is all consumed, it theoretically should give me this much product. But that's not always the case. And we'll see a few problems here. Here's an example. Once again, we're going back to the acid-base reaction with HCl and NaOH. If you use 2.4 grams of NaOH to neutralize 3.7 grams of HCl, and you produce 1.1 grams of NaCl, what is the percent yield of the reaction? The first thing we need to do, I know I'm sounding like a broken record, but we need to write down the reaction and figure out if it is balanced. And this was balanced because it's all, they're +1 and -1 ions, so the charge is balanced and I don't have to do anything else to balance the equation. So my equation is balanced. I need to convert these amounts from grams to moles, and we've already done that. We know 2.4 grams of NaOH divided by the molar mass gives me 0.06 moles of NaOH. We also know that 3.7 grams of HCl divided by 36.46 grams gives me 0.101 moles of HCl. Now I have the amount of moles, and as I said earlier, because this is a 1-to-1 ratio, I know that my NaOH is going to run out first, and it's going to only make 0.06 moles of NaCl. Here it is, this is supposed to be NaOH. 0.06 moles of NaOH. Oh, wait. I already did. I'm just converting it. Never mind. I thought I had one extra step here, but I don't. So 0.06 moles of NaOH, I know will give me 0.06 moles of NaCl because it's a 1-to-1 ratio. Now I have to convert this amount of moles of NaCl to grams of NaCl so I can find the percent yield. Percent yield is only found from mass in grams, not in moles. I can do that by knowing the molar mass of NaCl, which is about 58.44 grams. 0.06 moles of NaCl. I know that 1 mole of NaCl weighs 58.44 grams. My moles of NaCl will cancel out. I'm left with grams on top. 0.06 multiplied by 58.44 gives me 3.51 grams of NaCl. What does this tell me? This tells me that if I have 2.4 grams of NaOH, because it is my limiting reagent, if all of that mass reacts to produce NaCl, I should be getting 3.51 grams of NaCl. This is theoretically what I should be getting. So anything you calculate from the balanced chemical equation, etc., anything of that sort, will give you the theoretical yield, theoretical mass. Now, what does it tell me though? The problem tells me that you produce only 1.1 gram of NaCl. See the difference? I'm supposed to produce about, 3 times as much, at least, but I only collect in lab. So I went and did the experiment in laboratory, and I only collected at the end 1.1 grams. So what is my yield? This is the percent yield. This is the formula for percent yield. I take the actual yield or experimental yield, which will be given to you, so 1.1 grams, divided that by the theoretical yield, which is what I calculated from my balanced chemical reaction. See, I calculated I should be getting this much, but I only got that much. Multiplied by 100. So here's how I set it up. I have the experimental up on top, 1.1 gram, divided by the theoretical or the calculated at the bottom, 3.51, multiplied by 100%, gives me about 31%. Now, if you had these two numbers flipped, you would get a percent yield that was larger than 100%, which is not true. You never can get yields that are above 100% unless you have impurities or something else. That is not possible. So you know if you get a percent yield that is larger than 100, you would know that you flipped these two around. So then put the smallest amount on top and the larger amount at the bottom, and multiply by 100 would give you a number that is less than 100%. I will be showing you some other problems where you might have a percent given. So I could also say if you use 2.4 grams of NaOH to neutralize 3.7 grams of HCl, and you have a 31% yield, what is the actual yield of this reaction? So this would be X, and you would be given the percent yield, 31%, and asked to find the actual yield. You could do that. You could find the calculated one, and then you could go over here and figure out. So you could use this reaction to find any of these amounts, and I will be doing some of those types of problems so you can see how to work out the other types as well. But this is the last part that we're going to talk about for chapter 7. This is the end of chapter 7. If you have any questions, please reach out to me and email me. I know that this is kind of difficult. It's not what we signed up for, but this is the times that we live in, and we have to make the best of it. So let me know if you have any questions. Thank you.